How could people survive in homes made of wood and earth when everything outside froze solid? When temperatures plunged tens of degrees below zero, when icy winds stripped the warmth from any exposed surface in seconds, when winter darkness lasted for months and the world became a frozen killing field. We imagine Viking settlements buried under snow, battered by Arctic storms, barely clinging to survival. But the truth is far more remarkable. These communities didn't just survive the harshest winters in human history. They thrived. Their homes stayed warm, their families remained healthy, and their settlements continued functioning even when everything outside froze. Before we reveal exactly why Viking homes could maintain warmth in conditions that should have been impossible to survive, drop a comment with where you're watching from. And if stories of ancient survival technology fascinate you, hit that subscribe button, because what you're about to learn will change everything you thought you knew about Viking life and medieval engineering. The secret wasn't magic or superhuman endurance. It was remarkably effective engineering where every single element of the house, from foundation to roof peak, from wall construction to interior layout, was part of a unified heat preservation system. Vikings didn't build houses. They built thermal fortresses designed in perfect harmony with the brutal nature of the northern climate, turning what should have killed them into something they could not just endure but actually control. Their homes were warmer than many modern buildings. Not because they burned more fuel or worked harder to stay warm, but because they understood principles of heat retention, thermal mass, and natural insulation that most contemporary architects have forgotten. They created structures that worked with physics rather than fighting it, that used the environment itself as part of the heating system, and that required remarkably little energy input to maintain comfortable temperatures even when everything outside was frozen solid. Watch this to the end to find out how Vikings managed to turn the frosty enemy into their ally, why their engineering solutions were more sophisticated than they appear, and what specific techniques allowed them to create warmth in the heart of winter when neighboring peoples were freezing to death in their own shelters. The Viking longhouse wasn't just a building, it was a living, breathing organism designed for one purpose: preserving human life in conditions that killed the unprepared. Scandinavians who spent half their lives at sea building ships that could survive Atlantic storms transferred those same engineering principles to land, creating an architectural form unlike anything else in medieval Europe. These houses reached extraordinary lengths. 30 meters was common, some exceeded 80 meters, but their most remarkable feature wasn't size. It was shape. The walls curved gently like the sides of a dragon ship, and this wasn't aesthetic choice. It was calculated engineering to combat the merciless northern winds that could strip heat from a structure in minutes. Flat walls perpendicular to wind create resistance, forcing wind to slam directly into the surface and probe every gap for weakness. Curved walls deflect wind, allowing air currents to flow around the structure rather than hammering against it with full force. The same principle that made Viking ships fast and seaworthy made their houses wind-resistant and thermally efficient. The entire life of the community concentrated under one giant roof. There was no division into separate rooms in the modern sense. The clan leader, his family, relatives, workers, and even enslaved people all lived in this single massive space. This wasn't just social structure, it was crucial thermal engineering. Dozens of people in one enclosed space generated significant amounts of metabolic heat. Every human body produces roughly 100 watts of thermal energy continuously. 20 people together generate 2,000 watts, equivalent to running 2 electric space heaters constantly. Except this heat source required no fuel and never stopped working. The communal living that defined Viking social structure was simultaneously a brilliant heating strategy. The longhouse was designed as a self-sufficient ark capable of withstanding months of winter isolation. Its construction followed specific orientation principles to minimize heat loss. The building's long axis typically ran east-west, presenting the minimum surface area to the brutal north winds that dominated Scandinavian winters. Entrances were almost never positioned on the short end walls that bore the brunt of weather. Instead, they were hidden in the long sidewalls, often with special extensions or covered vestibules that created airlocks preventing direct wind penetration into the living space. Every architectural decision had thermal purpose. The walls of this earthship were massive, multi-layered structures that reveal the true sophistication of Viking engineering. They didn't rely solely on wood, which was valuable in the harsh climate but actually not the best insulator. Instead, they created complex assemblies of materials where each layer performed a specific function, transforming the dwelling into something resembling a modern thermos bottle. This technology had been refined over centuries of brutal trial and error where design failures meant death. The knowledge was hard-won, tested by generations who learned which techniques preserved life and which led to frozen corpses discovered when spring finally arrived. Now, if you're already fascinated by this lost engineering, make sure you're subscribed because we're about to reveal the specific construction techniques that made these thermal fortresses actually work. When we hear Viking house, we imagine log cabins similar to those built in forested regions of Europe. But this assumption is completely wrong and misses the true genius of Norse construction. In many Viking territories, especially Iceland, Greenland, and the treeless regions of northern Norway, wood was incredibly scarce, sometimes completely unavailable. This scarcity forced Vikings to develop building technology that minimized wood use, relying instead on materials that were abundant and, remarkably, more thermally effective than timber. What they created was superior to wooden construction in almost every way that mattered for survival. The foundation of the house was a wooden frame. This was the only part where timber was truly indispensable. Strong pillars made of oak, pine, or birch formed the skeleton, the load-bearing structure that supported the enormous weight of the roof and walls. These posts, often made from entire tree trunks, were dug deep into the ground for stability. But the walls themselves were not wooden in any conventional sense. They were earthen walls, and this was the main secret of their extraordinary thermal efficiency. Before erecting the frame, Vikings prepared the foundation with meticulous care. They laid out lines of large, flat stones around the entire perimeter of the future house. This stone belt served two critical functions that reveal sophisticated understanding of building science. First, it leveled the ground, creating a stable platform for construction. But second, and far more important for thermal performance, it insulated the wooden frame from damp earth, preventing the wood from rotting and failing. Moisture is the enemy of any building material, and Vikings understood that keeping structural elements dry was essential for long-term durability. Wooden posts were positioned on this stone foundation, and then came the revolutionary element. The space between posts was filled with the most important insulation material of the Viking era: turf. Turf, also called peat in some regions, consisted of layers of earth tightly bound together by dense grass root systems. It was cut from marshy areas in large rectangular blocks similar to enormous bricks. These blocks could weigh 20 to 30 kilograms each, and constructing a single longhouse required thousands of them, representing weeks of hard labor cutting, hauling, and stacking. These turf bricks were stacked methodically to form walls of incredible thickness. The measurement at the base could reach 1.5 meters, sometimes even 2 meters, thicker than the walls of many medieval stone castles. The wall tapered slightly toward the top, which gave it structural stability and helped shed water. The blocks were often laid in herringbone patterns or interlocked like masonry to ensure maximum density with no gaps where cold could penetrate. This wasn't random stacking, it was careful construction following principles that had been refined over generations. The thermal properties of these turf walls were phenomenal, and understanding why requires knowing some basic physics. The secret wasn't the earth itself. Soil actually conducts heat fairly readily. The insulation came from the structure of the material. Turf's porous composition, permeated with thousands of tiny grass roots, created countless small air pockets throughout the material. Air, specifically trapped, motionless air, is one of nature's best insulators. It's the same principle behind modern fiberglass insulation, foam boards, and down jackets. Trap air in small pockets, prevent it from moving, and you create a thermal barrier. A 1.5-meter thick turf wall contained millions of these tiny air pockets, creating an insulation barrier far more effective than solid wood or stone of equivalent thickness. Heat trying to escape from inside had to work its way through this complex maze of material and trapped air, a journey that took hours rather than minutes. But turf had another remarkable property. It was a living material. In spring, the exterior surface of these walls would sprout fresh grass, transforming the house into what looked like a natural hillside. The structure blended completely with the landscape, becoming almost invisible from a distance. This grass covering wasn't just camouflage. It served critical functions. The new growth sent roots down into the turf blocks, binding them together even more tightly than the original construction. The living grass layer also helped manage moisture, absorbing rain before it could penetrate into the wall structure and transpiring excess water back into the atmosphere. The house literally became part of the earth, growing and adapting with the seasons. In summer, the grass was green and lush. In winter, it died back, but the dense root mat remained, continuing to bind the structure together and trap insulating air. This combination of materials, wooden frame for structure, stone foundation for moisture protection, and massive turf walls for insulation, created a building envelope far more sophisticated than it appeared. Vikings had essentially invented composite construction, using multiple materials in combination to achieve properties that no single material could provide. But the walls were only part of the thermal system. What Vikings did with the interior space reveals even more remarkable understanding of heat management and survival engineering. What I'm about to reveal was completely normal for Vikings but seems shocking to modern people accustomed to separating living spaces from animals. They shared their homes with dozens of livestock. This wasn't primitive ignorance or desperate poverty. It was ingenious engineering that saved enormous amounts of fuel and allowed survival through winters that would have otherwise been impossible. The longhouse wasn't just a dwelling for people. It was also a winter barn, and these two functions were inextricably linked in a way that demonstrates sophisticated understanding of thermodynamics. The interior space was clearly divided into two zones, living area and working area. Approximately half, sometimes more than half, of the total house area was occupied by stalls for livestock. Cows, sheep, goats, and horses representing the main wealth of any Scandinavian family spent the entire winter indoors. The absence of separate barn buildings wasn't laziness or lack of building materials. It was calculated survival strategy based on perfect understanding of how large animals generate heat. The living area and the livestock area were usually separated by a simple wooden partition. But this partition wasn't airtight or insulated. It was essentially a symbolic boundary that marked the division while allowing air and heat to circulate freely between both sections of the house. People and animals breathed the same air under the same roof, lived in the same thermal envelope, and benefited from each other's warmth. The arrangement was symbiotic in the truest sense. The physics was straightforward and remarkably effective. Any large mammal, a cow for instance, generates enormous amounts of metabolic heat simply by existing. A single adult cow produces roughly 1,500 to 2,000 watts of heat continuously, equivalent to running a large space heater 24 hours a day. A dozen cows together, a typical number for a prosperous Viking household, generated 20,000 watts or more of constant heat. This was a complete heating system operating around the clock, requiring no fuel, no maintenance, and producing warmth as a free byproduct of the animal's normal metabolism. The heat generated by livestock was as critical a resource as firewood or peat for the hearth fire. In the coldest months, the animal's contribution might represent half or more of the total heat keeping the household alive. The floor level in the living area was often constructed slightly higher than the barn section. This wasn't primarily about hygiene, though it did help prevent waste from flowing into human living space. The elevation difference served a thermal purpose. Warm air rises, basic physics that Vikings understood perfectly through observation. Heat generated by the animals, following natural convection, rose and moved toward the higher living platform. This created a gentle but constant flow of warmth from the livestock area into the human living space, mixing with heat from the central hearth to create comfortable temperatures throughout the structure. The animals benefited equally from this arrangement. In the harsh Scandinavian climate, a separate barn building would freeze completely, with interior temperatures barely different from outside. Livestock kept in such conditions faced serious cold stress, reduced milk production, higher mortality, and potential freezing death during the worst storms. By housing animals under the same roof as humans, sharing the warmth from the hearth and benefiting from the overall thermal envelope of the massive insulated walls. The livestock remained protected and productive through the entire winter. It was genuine symbiosis where both species benefited from proximity. Of course, this living arrangement had obvious drawbacks. The primary one was smell. Dozens of large animals confined indoors for months produced odors that would be intolerable to modern sensibilities. But for people of that era, accustomed to livestock as daily reality and to the general smells of pre-industrial life, this was acceptable trade-off. Warmth and survival mattered far more than olfactory comfort. Vikings made a conscious choice: share space with animals and live, or separate for comfort and risk freezing. The choice was obvious. Additionally, the constant operation of the central hearth with its smoke helped neutralize odors to some degree. The smoke permeating the entire structure had antibacterial properties and masked some of the animal smells with the scent of burning wood or peat. This human-livestock integration represents one of the clearest examples of Viking practical genius. They observed that animals generated heat. They understood that heat was scarce and valuable in winter. They designed their buildings to capture and utilize that biological heat source rather than wasting it. The solution was simple, effective, and required no technology beyond basic construction, just observation and willingness to adapt living arrangements to physical reality. But animals and hearth fires still weren't enough without proper building design to trap and preserve that precious warmth. And the final critical element involved something that seems like a weakness but was actually brilliant engineering: the almost complete absence of windows. The main enemy of any warm home in the north isn't the cold itself, it's the wind. Wind strips precious heat away through the smallest cracks, creates drafts that make interior temperatures plummet, and defeats even the best insulation if it can penetrate the building envelope. The entire architecture of the Viking longhouse was designed with one primary purpose: minimize uncontrolled air movement at all costs. The first thing that shocks anyone studying authentic Viking longhouses is the almost complete absence of windows. This seems primitive to modern eyes accustomed to natural light and views, but it was calculated engineering based on perfect understanding of heat loss. Glass was incredibly rare and expensive in the Viking Age, available only for churches and the wealthiest nobles, never for common dwellings. Ordinary houses were completely deprived of this luxury. Occasionally, tiny slits might be cut into walls for minimal ventilation or light, but in winter these openings were tightly plugged with moss, straw, or carved wooden blocks sealed with clay. Life in a Viking longhouse took place in constant semi-darkness, dispelled only by the flickering flames of the central hearth and perhaps small oil lamps made from soapstone or clay. This was a conscious sacrifice made for survival. Vikings understood with perfect clarity that any window was fundamentally a hole in the thermal armor of their home, a weak point where precious heat could escape and deadly cold could enter. They preferred darkness to cold. They chose survival over comfort. And in the conditions they faced, this wasn't extremism, it was rational calculation. Modern building science confirms their instincts were correct. Even with double-pane or triple-pane glass and insulated frames, windows remain the weakest thermal element in any building. A single modern window can account for 25 to 30% of a home's total heat loss. In a structure heated only by fire, with no backup systems, that level of heat loss could mean the difference between survival and death. Vikings couldn't afford that weakness, so they eliminated it entirely. No windows meant no thermal weak points, no drafts, no places where frost could penetrate. The building envelope remained intact. For lighting and limited ventilation, Vikings sometimes used special roof openings, but these were carefully designed and controlled, not random holes. We'll discuss them separately, but the principle was the same. Any opening was a potential disaster that had to be minimized and managed carefully. If windows were the thermal weakness Vikings eliminated, doors were the vulnerability they couldn't avoid but worked ingeniously to minimize. Every dwelling needs entrances, but entrances are fundamentally problems, gaps in the protective envelope that must open regularly, allowing freezing air to rush in and warm air to escape. Vikings developed sophisticated solutions to neutralize this threat. The doors themselves were always positioned low, so low that a modern person would have to bend significantly to enter. Adults routinely had to duck and sometimes crouch to pass through. This design served multiple purposes. It forced visitors to bow upon entering, showing respect to the household, a social function. But more importantly, it minimized the volume of cold air that could enter when the door opened. A low doorway created a physical barrier that blocked much of the icy draft that would otherwise rush in at head height. The doors themselves were massive structures made from thick wooden planks fitted tightly together. They didn't hang on metal hinges like modern doors. Instead, they rotated on heavy wooden pins that fit into precisely carved grooves in the threshold below and the frame above. This pin-and-socket system allowed the door to swing while maintaining extremely tight fit all around the edges. The door jambs were carefully shaped to create overlapping surfaces where the door pressed against the frame when closed. This overlap, combined with the door's weight, created an effective seal that prevented drafts. Sometimes animal hide or wool was stuffed into any remaining gaps for additional sealing. But the true brilliance of Viking door design was the vestibule or entrance hall system, what modern engineers would call an airlock. The main entrance to a longhouse wasn't a single door opening directly into the living space. Instead, a small vestibule was built in front of the primary door, creating a two-door system with an unheated buffer space between them. When someone entered from outside, they first passed through the outer door into this small vestibule, then closed that door behind them before opening the inner door to the heated living area. This airlock system was devastatingly effective at preventing heat loss. The physics are simple but powerful. When the outer door opens, cold air enters only the small vestibule space. When that door closes, the cold air is trapped in the unheated buffer zone. When the inner door then opens, the air entering the living space is cold, yes, but it's not the full blast of exterior Arctic wind, it's air that's already been somewhat moderated by being inside a structure. More importantly, the two-door system prevented through drafts. Wind couldn't blow directly from outside into the heated interior because it had to pass through two separate barriers with the vestibule space breaking the direct pathway. While a person stood in the vestibule, they also had time to shake snow from their clothes and remove ice-encrusted outer garments. This meant moisture and cold remained in the buffer zone rather than being carried into the living space where it would melt and create humidity problems. The positioning of entrances was equally calculated. Doors were almost never placed directly opposite each other, which would create a direct wind tunnel through the house when both were open. Most often, entrances were positioned in the long walls rather than the end walls, and they faced away from prevailing winter winds. Sometimes the entrance was additionally protected by a protruding section of wall or an earthen embankment piled against the building. These windbreaks deflected the worst gusts away from the door area, further reducing the assault of cold air when anyone entered or exited. Every detail, door height, construction, operation, positioning, vestibule design, represented accumulated knowledge refined over generations. Vikings who built carelessly, who didn't seal their doors properly, or who positioned entrances poorly, suffered through colder winters and sometimes didn't survive. Those who built well lived comfortably and passed their knowledge to their children. The heart of warmth, the long fire. At the center of the longhouse, running along its entire central axis, was the langold, the long hearth. This was the beating heart of the entire structure, the sole source of heat and light that made life possible during the months of frozen darkness. Unlike compact fireplaces or stoves positioned against walls, the langold was an elongated shallow pit that could stretch 10, 15, even 20 meters through the length of the building. This wasn't a fireplace in the modern sense. It was a continuous fire channel running through the core of the living space. The hearth wasn't simply a depression in the floor. Its construction was careful and intentional. The edges were lined with large flat stones carefully selected for their ability to withstand repeated heating without cracking. These stones served multiple critical functions that reveal sophisticated engineering. First, they contained the fire, preventing it from spreading across the earthen floor and potentially igniting the wooden structure above. Fire control was literally life or death important in a dwelling made substantially of flammable materials. Second, and more remarkably, the stones functioned as massive thermal batteries. Throughout the day as fire burned, these stones absorbed enormous quantities of heat. A large flat stone heated for hours stores incredible thermal energy. Then, slowly and steadily through the night, the stones released that stored heat back into the living space. This thermal mass effect meant the longhouse didn't depend entirely on active burning fire for warmth. The heated stones continued radiating heat for 8 to 12 hours after flames died down, maintaining comfortable temperatures through the night without requiring someone to constantly feed the fire. The fuel varied by region. In forested areas of Norway and Sweden, wood was the primary fuel, birch and pine providing good heat output. But in treeless regions like Iceland and Greenland, peat was essential. Peat, partially decomposed organic matter cut from bogs, burned slowly and steadily, producing even heat over long periods. Harvesting peat for winter was one of the community's most important tasks. Families would spend weeks during summer cutting peat blocks, stacking them to dry, and hauling them to storage. Survival depended directly on accumulating sufficient fuel to last through the 6 to 8 month winter when gathering more would be impossible. The Langold's elongated shape was brilliantly suited to the longhouse's architecture. A conventional round hearth positioned at one end of an 80-meter building would heat only the immediate area, leaving the far end freezing and uninhabitable. The long fire distributed heat evenly along the entire length of the structure. People sitting on benches along the walls all received their portion of warmth from the nearest section of this central heater. Nobody was left in a cold zone too far from the heat source. The design ensured thermal equity. Everyone benefited equally from the fire's warmth. But the Langold wasn't only a heating system. It was multifunctional in ways that reveal how completely Viking life centered around fire. The hearth provided the only source of illumination in the windowless house. Flickering flames cast dancing light on carved wooden pillars, on faces of family members, on the smoke-darkened beams overhead. All social life, all work that required light, all evening activities concentrated in this illuminated zone around the central fire. The Langold was also the kitchen. Large iron or soapstone cauldrons hung from chains suspended from ceiling beams or sat on iron tripods positioned over different sections of the fire. Soups and porridges simmered for hours. Meat and fish roasted on spits. Flatbread baked on hot stones at the fire's edge. The smell of cooking food mixed with wood smoke and the ever-present animal odors from the barn section, creating the distinctive atmosphere of a Viking dwelling, a smell that would have been instantly recognizable to anyone who'd ever lived in such a house. The fire was sacred in more than metaphorical sense. It represented life. An extinguished hearth in winter was catastrophe that could kill everyone in the household within hours. Maintaining the fire was constant vigilance, usually the responsibility of women and older children who fed wood or peat, managed cooking, and ensured the flames never went completely out. But fire creates smoke, and smoke presented a serious challenge that Vikings solved with characteristic ingenuity. Managing smoke without chimneys. The presence of an enormous open hearth in the center of the dwelling created an immediate problem. How to remove smoke and combustion products without losing all the heat that made the fire valuable in the first place. The solution Vikings developed was as simple as it was effective. The brick chimneys and flues familiar to modern people didn't exist in the Viking Age. Smoke from the Langold rose freely according to basic physics. Hot gases are less dense than cold air, so they naturally rise. The smoke accumulated in the upper portion of the house, creating a dense, hot, acrid layer above human head height. The entire upper space of the longhouse, roughly the upper third of the interior volume, was perpetually filled with smoke. This created a clear stratification, relatively clear air at floor level and bench height where people lived, and thick smoke in the rafters and roof space. This constant smoke saturation had an unexpected beneficial effect that Vikings certainly understood even if they didn't describe it in modern chemical terms. The The smoke and soot continuously saturated the wooden beams, rafters, and roof timbers. This process, essentially smoking the structural wood from the inside, was an excellent preservative. The chemicals in wood smoke, particularly creosote and various phenolic compounds, are toxic to wood-boring insects and inhibit fungal growth that causes rot. By smoking their own structural timbers constantly, Vikings dramatically extended the lifespan of their buildings. Longhouses could last 50 to 100 years or more, far longer than unsealed wooden structures would typically survive. But smoke had to exit eventually, and this is where the lyra, the smoke hole in the roof, became critical. At the highest point of the roof, directly above the langled, a special opening was constructed. This wasn't simply a hole chopped through the roof. It was a carefully designed feature with specific construction and control mechanisms. The lyra typically consisted of a wooden frame built into the roof structure, creating an opening that could be partially or completely covered. A movable wooden panel or cover sat over this frame, controlled by a long pole that extended down to floor level near the hearth. Managing this smoke hole was genuine skill requiring constant attention and judgment. The person tending the fire also managed the lyra, adjusting it throughout the day based on fire intensity, wind conditions, and temperature. In winter, the lyra was kept almost completely closed, leaving only a small gap. This allowed the thickest smoke to escape, enough to prevent the living space from becoming completely unbreathable, while retaining as much warm air inside as possible. The smoke layer under the roof acted as insulation itself, trapping heat that would otherwise escape. The adjustment was a delicate balancing act. Close the lyra too much, and the house filled with choking smoke that made breathing difficult and eyes burn. Open it too wide, and precious warm air rushed out, requiring more fuel to maintain temperature. Finding the right balance required experience and constant adjustment. During intense fire use, when cooking or when heating the hearthstones for overnight warmth, the lyra would open wider to allow increased smoke volume to escape. When the fire died down to coals, it would close nearly completely, conserving maximum heat. The lyra also provided the dwelling's only source of natural daylight beyond the open door. A small shaft of weak winter sun might penetrate through the smoke hole, creating a dim beam in the smoky interior. It wasn't much light, but it provided some connection to the outside world and helped inhabitants track the passage of time during the long polar winter. Vikings sacrificed air quality for warmth. The interior atmosphere of a longhouse was smoky, hazy, and by modern standards quite polluted. But the alternative, cold, clear air and dead inhabitants, made the choice obvious. The living roof, nature as insulation. The roof of a Viking longhouse was just as critical for thermal retention as the massive walls, and its construction revealed the same sophisticated multi-layer approach. The roof structure began with a strong wooden rafter system, heavy beams extending from the top of the wall frames to a central ridgeline. On these rafters, thinner poles or rough boards created a wooden deck that formed the base layer. But this wooden layer alone provided almost no insulation and minimal water resistance. The real protection came from what was built on top. The next layer was waterproofing, and Vikings used one of nature's perfect materials, birch bark. Birch bark was carefully harvested in large sheets, removed from trees in sections that could be 1 to 2 meters long. This bark was laid on the wooden decking like shingles, overlapping so water would run downward without penetrating inside. Birch bark contains natural resins and oils that make it virtually waterproof and resistant to decay. It remains flexible even when dried, doesn't crack easily, and can last decades before requiring replacement. It was ideal roofing material where it was available. On top of the birch bark waterproofing came the primary insulation layer, turf. Using the same earthen root blocks employed in wall construction, Vikings laid 2 or even 3 complete layers of turf across the entire roof surface. This earthen cap was monumentally heavy. A large longhouse roof covered in turf could weigh 20 to 30 tons or more. This required the wooden frame to be incredibly robust, but the thermal benefits justified the structural engineering challenge. The turf roof served multiple simultaneous functions that demonstrate integrated design thinking. First, it was superb insulation. Like the walls, the porous structure with its trapped air pockets prevented heat from escaping upward, the direction heat naturally wants to go since warm air rises. A thick earthen layer reflected heat back downward into the living space. Second, the turf protected the fragile birch bark layer from mechanical damage, from falling branches, from people walking on the roof to make repairs, from animals that might scratch or tear it. The earth provided a tough protective shell for the waterproofing beneath. Third, the turf roof was literally alive. Within weeks of construction, grass seeds in the soil would germinate. The roof would turn green, sprouting grass that grew vigorously during the brief northern summer. The house became indistinguishable from a natural hillside, blending completely into the landscape. This wasn't merely aesthetic. The living grass sent roots downward into the turf blocks, binding them together even more tightly than the original construction. The root mat created a unified, monolithic layer that resisted erosion, held moisture appropriately, and grew stronger over time. During summer, this grass could be grazed by sheep or goats who would climb onto the roof to eat the fresh growth. This provided food for livestock while simultaneously maintaining the roof. The animals grazing kept grass at optimal length and their hooves compacted the soil, improving its water resistance. The roof pitch was carefully calculated, steep enough to shed water effectively but not so steep that turf would slide off or that snow couldn't accumulate, snow accumulation being beneficial, as we'll see. The typical pitch created a gentle slope that looked almost like a natural hillside. This living, breathing roof completed the thermal envelope around the longhouse. Combined with massive turf walls, minimal windows, controlled entrances, and the heat sources inside, it created a complete system that trapped warmth with remarkable efficiency. But Vikings had one more trick for thermal protection. They weaponized winter itself. Snow, the free insulator. While heavy snowfall is a problem for modern buildings requiring dangerous roof clearing and causing structural stress, Vikings understood snow as a powerful ally in their struggle against cold. They didn't fight snow accumulation, they encouraged it and used it as free, incredibly effective insulation. The very design of the longhouse was intended to catch and hold snow. The long sloping roof transitioning smoothly into thick turf walls had no sharp corners or edges where snow would slide off easily. When winter storms arrived, the building's shape caused snow to accumulate naturally. Wind patterns around the curved walls created drifts that piled against the structure. Snow accumulated on the gentle roof slope, building up in thick layers. As winter progressed, the longhouse gradually disappeared under a deep blanket of white. The drifts against walls could reach all the way to the roofline, completely covering the earthen walls. The roof itself might be buried under 1 to 2 meters of compacted snow. From outside, the settlement transformed into a landscape of smooth white mounds from which only smoke vents and entrance vestibules remained visible. Vikings made no effort to dig their houses out from under this snow burial. In fact, they understood perfectly that snow was one of the best natural insulators available. The secret lies in snow's structure. Fresh snow is approximately 90 to 95% trapped air. Individual ice crystals create a lattice with vast amounts of air space between them. This trapped air, prevented from moving by the crystal structure, provides excellent insulation. The principle is identical to modern foam insulation or down feathers. Trap air, prevent convection, and you create thermal resistance. A layer of compacted snow 1 meter thick or more created an additional thermal cocoon completely surrounding the house. This cocoon sealed the dwelling, covering the last tiny gaps where wind might have penetrated, and added another complete insulation layer on top of the already thick turf walls. Under this snow armor, the temperature at the surface of the walls and roof remained stable near 0 degrees Celsius even when blizzards raged outside and air temperature dropped to -30 degrees Celsius or lower. The snow acted as a buffer, smoothing out extreme temperature swings and protecting the structure from the worst cold. This created a multi-layer defense system. The innermost layer was the wooden frame and living space. The second layer was the thick turf walls and roof. The third outer layer, present only in winter, was the massive snow blanket. Each layer contributed to thermal protection, working together to create a fortress that could maintain interior warmth even in the most brutal conditions. The complete system, integration and survival. The genius of Viking longhouse design wasn't any single element. It was how everything worked together as an integrated system where each component reinforced the others. Start with the heat sources. Metabolic warmth from dozens of humans, biological heat from livestock, and fire from the langold. These three sources provided the baseline thermal input. That warmth was trapped by the building envelope. Massive turf walls, living turf roof, minimal openings, controlled entrances with airlocks, and in winter, the additional snow layer. Each barrier prevented heat escape. The interior layout maximized heat utilization. The raised benches kept people above the coldest floor-level air. The central position of the langold distributed heat evenly. The open barn connection allowed animal warmth to circulate, and the smoke layer under the roof provided additional insulation. Even small details contributed. The low doorways blocked drafts. The stone lining of the hearth stored thermal mass. The smoke-saturated timbers resisted decay, and the grass-covered roof managed moisture while strengthening structure. This wasn't primitive construction. It was sophisticated engineering that understood thermodynamics, material properties, structural requirements, and the behavior of heat, air, and moisture. Vikings created buildings that maintained interior temperatures 20 to 30 degrees Celsius warmer than exterior conditions while requiring relatively modest fuel input. The result: while everything outside froze solid, while neighboring peoples struggled and sometimes died in their inadequate shelters, Viking homes stayed warm. Families slept comfortably on the raised benches. Children played near the hearth. Work continued through the long dark winter. Life persisted in conditions that should have been impossible. Why did Viking homes stay warm while everything outside froze? Because Vikings understood that survival required working with nature rather than fighting it. They used earth as insulation, snow as additional protection, animal heat as a free resource, and careful design to trap every bit of warmth. They built thermal fortresses that were more sophisticated than they appeared. Living structures that grew grass, breathed with the seasons, and maintained life in the Arctic winter using nothing but natural materials and accumulated knowledge. Modern buildings with all their technology often can't match this performance. We heat our homes by burning massive amounts of fuel or consuming huge quantities of electricity, fighting inefficiency with brute force rather than preventing heat loss through intelligent design. The Vikings solved the problem differently. They built once, built well, and created structures that required minimal energy input to maintain comfort. Their knowledge deserves to be remembered. If this revelation about Viking thermal engineering fascinated you, hit that subscribe button because there are countless more forgotten technologies from ancient civilizations that modern society needs to rediscover. Drop a comment telling me which historical survival technique you want us to investigate next, because our ancestors solved impossible problems with brilliant simplicity, and their wisdom deserves to be preserved.